In this video, we're going to discuss quantization and photons. Now, in the previous video, we talked about black-body radiation, and we looked at this black-body radiation curve. And we learned that Max Planck found a mathematical formula that fit the experimental radiation curve that you see here. He proposed something revolutionary. He proposed that atoms do not emit or absorb light continuously, which is based on classical theory, but they do in little chunks or bundles or packets of energy. He called these discrete amounts of energy quanta. Or if you think of it as one single chunk of energy, you can call it like a quantum. He still believed that light existed in continuous waves, but the difference is that it was emitted and absorbed in quantum chunks. You see, this idea of quantization we've already discussed earlier in the course. Remember when we talked about electric charge? We learned that a charge object can only come in a multiple of the charge of an electron, which is 1.6 to the power of negative 19 coulombs. You may recall this formula, Q equals N times E, where N is the number of electrons and E was the charge of an electron. So a charged object with charge Q would be always a multiple of E. You couldn't have like 1.5 electrons. So that's the idea of quantization. On a small side note, it's interesting to note that Planck publicly refused to believe his own theory, and he makes mention of using this equation until a better idea is found. Well, then Einstein came along, and he went further, and he proposed that light itself is composed of quanta. The quanta of light energy was later given the name photon, coming from Einstein. But what are photons? How fast do they travel? And do they have mass? Well, they don't have any mass. They're massless. We say it has no rest mass. And the word rest comes from relativity. And essentially I'm saying that all photons travel at the speed of light, which is equivalent to 3 times 10 to the power of 8 meters per second. Well, how do you calculate the energy of a photon? Well, that comes back to Max Planck. E equals hf. The energy of a single photon is equivalent to h, which is a constant. That's Planck's constant here, which is equivalent to 6.626 times 10 to the power negative 34 in joules seconds, multiplied by the frequency measured in hertz. So you can see from this formula conceptually that the energy is directly proportional to the frequency, which means like a red photon, which has a longer wavelength and a lower frequency, will be less energetic than a blue photon, which has a shorter wavelength and a higher frequency. So the higher the frequency, the more energetic the photons are. I always kind of think back to lasers and think I've got a red laser, and you could also sometimes buy a green laser. That green laser has more energy per photon. It's probably more damaging to your eye if that were to go into your eye. So, light consists of bundles or discrete packets of massless units which we call photons. And a photon travels at the speed of light in a vacuum. Although photons seem to have no mass, they do carry momentum with them. To calculate the momentum of a photon, we use the following equation. Rho equals h, Planck's constant, divided by the wavelength in meters or nanometers. Do not attempt to use the equation rho equals mass times velocity, because remember, photon doesn't have a mass. Now, since photons travel at the speed of light, we can replace v with c in the wave equation. If you combine E equals hf and C equals f times lambda, we'll just rearrange the frequency to write it as C divided by lambda and substitute it in here. Then we get another version of Planck's equation. E equals hc all over lambda. And you may notice that h over lambda over here is equivalent to the momentum. And so therefore you can write this equation E equals the momentum times the speed of light. These 4 boxed equations are listed on your AP formula sheet. There are a couple common areas that people tend to make mistakes. One, they might think of a photon as being something that has mass and use the classical equation of momentum equals mass times velocity. That would be wrong to do that. Another thing that people typically make as a mistake in here is they're not careful with units. You see, the energy we can write in terms of joules, or you can also write it in terms of electron volts. If you go to the next page, you'll see us talking about over here the electron volts. 1 electron volt is equivalent to 1.6 times 10 to the power negative 19. So if you are, and it's often convenient to write something in electron volts instead of a joules, because you can see you'll often with photons get very small amounts of energy. So what we do in a lot of our questions is we'll write our constant h, instead of being in joules seconds, you may want to write it in electron volts seconds. And then therefore your final answer will be in electron volts when you compute it. Furthermore, you have something like hc in here. You've got already Planck's constant multiplied by the speed of light and written in joules times meters. And nicely written over here on the right side, they've written in terms of electron volts times nanometers. Why? Well, let's say they give you a question that has something in electron volts over here, and you want a wavelength that's not in meters, but in nanometers. So if you use this constant here with the energy in electron volts, you'll end up an answer with nanometers. So be careful with units. I would highly advise to make sure that as you solve problems, you substitute your units in and make sure they're all canceling out appropriately. Okay, I think you're ready to get some practice with working with photons. Go on to the next example, example number 1.